Good afternoon. And today we will be dealing with a problem which is somewhat different from the previous two problems what we have already dealt in the previous classes, designing a Bode plot from a given transfer function. And here the problem will be having a quadratic function in your denominator and how to deal with a transfer function which is in the form of which is having a quadratic function or a quadratic factor or quadratic equation. Okay, how to deal with that, how to find the corner frequency and plot your Bode plot and find out your frequency domain specification. So at the end of this lecture, you will be able to plot a Bode diagram for a transfer function having a quadratic function. So that's the objective. So the given transfer function is g of s is equal to 75 into 1 plus 0.2s divided by s into s square plus 16s plus 100, and this s square plus 16s plus 100 is the quadratic function or quadratic equation, which has to be of the form a s squared plus bs plus 1. Okay, so the 100 which is available here has to be divided by the entire divided by 100. This equation has to be divided by 100 so that we get a form of this type. Okay, right. So before that, let us find what is the natural frequency and the zeta value from the for this quadratic function, and if you compare it with the standard form s square plus 2 zeta omega ns plus omega n squared, you get omega n is equal to 10 and zeta to be 0.8. This omega n is equal to 10 is going to be the corner frequency of this function. The corner frequency from this function, okay, you will get it like 10 radians per second. So as usual, we have to see, we have to deal with uh, the S domain transfer function has to be converted into a time constant form. So what I have to do, I will take this 100 outside. I will take this 100 outside. Then what happens here? You divide it by 100. So you will get s squared by 100 plus 16s plus 100. And this 100 goes, 100 is divided by 75. So probably 0.75 into 1 plus 0.2. So this is completely now completely a time constant form. Okay, now time constant form. So now the next work is I have to replace s is equal to j omega here. So I replace that and group my what is that real part and imaginary part. Okay, this is 1 minus 0.01 omega squared is my real part. Okay, and this is my imaginary part. Okay, for that particular quadratic function. Why I want this? Because when I am dealing with angle calculation, then I have to go for tan inverse of imaginary by real. So in that case, I need this real and imaginary to be segregated. And the second most important is this problem varies basically uh, in forming the angular equation, because if you see the tan inverse of the real part, imaginary part divided by the real part, for this particular quadratic part, okay, you get like the angle form is going to be this, and this particular term 1 minus 0.0 omega squared becomes 0 when omega is equal to 10. That is your undamped natural frequency. Omega n is equal to 10. Okay, if something becomes more than something becomes 0 in the denominator, okay, it becomes like an infinite factor, and tan inverse of infinity is always going to be 90. If you work on beyond this omega term, and the angle becomes an obtuse angle because it is more than 90 degree, and for that a correction of 180 plus has to be added. 180 plus this term, angular term, has to be added in this phase equation, where we take omega greater than omega n. Okay, in that case we have to add this 180 plus that. So the significance of this particular problem is how to choose a corner frequency. We have done it, and the second thing is how your angular equation is going to be different. how your angular equation varies, angle equation varies. That is being explained now. Okay, so okay, let us go step by step. The first thing is we have converted that into a sinusoidal transfer function. We have found out the corner frequencies. So one of the corner frequencies is available. What is that? 1 plus 0.2 s is there. 1 plus 0.2 s or 0.2 j omega. So omega c is equal to 1 by 0.2, which is equal to 5 radians per second. So let me choose omega c1 is equal to 5 radians per second, and this omega c2 is equal to omega n, which is equal to 10 radians per second, right? So two corner frequencies are there. So this is from 1 plus 0.2 j omega, this one, and this is from the quadratic function. This is from the quadratic equation. So my next step is I have to find the corner frequency less than the smallest corner frequency for the transfer function, and highest corner frequency than the second the largest of the corner frequency of the transfer function. So something has to be considered less than 5 radians, and some has to be considered above 10 actually. So omega L is taken as 0.5 radians per second, and omega H is taken as 20 radians per second as per the previous problems. We have also already seen that, we have considered that. So three terms are there. First term we will take 0.75 j omega. Okay, this 0.75 j omega, it doesn't have a corner frequency since it doesn't have a time constant. Since your j omega is in the denominator, you will have a minus sign, and the power of omega is 1, so you will get a 20. So minus 20 is your first slope, then there is no change in slope at the first term. Then based on the corner frequency's value, ascending order, we have to choose that. So the term which has to be chosen is 1 plus 0.2 j omega. So the corner frequency is 5 radians per second, and this omega is in the numerator, so it is plus 20, and the power of omega is 1, so it is remains 20. Already minus 20, this is plus 20, so if you add it, you get 0 decibels as a change in slope. Then you choose the third term, which is the quadratic function 1 by that quadratic equation, and we know that the corner frequency is 10 radians per second, and since the highest power of omega is of the power 2 and it is in the denominator, you will get a minus 40 there. And previously it is 0, now it is minus 40, so the change in slope is going to be minus 40. So this is how your first part is been done, and using this table and the corner frequencies available, we have to find what is the value of what is your values of magnitude. So if you choose omega is equal to omega L, which is equal to 0.5 radians per second here. So 20 log of the first term 0.75 by j omega, which is equal to 20 log of 0.75 by 0.5 will give you 3.5 decibels. The second term is omega is equal to omega C1. Omega C1 is equal to 5 radians per second. So the first slope in the table is going to be minus 20 log of the present value of the omega and the previous value of the omega plus this 3.5 decibels per second. So how much I will try to get it like 5 divided by 0.5 is going to be 1 or 10. Log of 10 is equal to 1 into minus 20 plus 3.5, which is equal to minus 16.5. Okay, which is equal to minus 16.5. Okay, log of 5 by 0.5 will give you 10. Log of 10 is 1. Minus 20 is multiplied with that value of 1. So minus 20 plus 3.5 will give me minus 60.5 decibels. In your textbook, which you normally follow, sometimes they may have used this form, or they might have taken this 20 log of the same thing again. By replacing that, you will get the same thing, right? Then omega is equal to omega C2, which is equal to omega n, which is equal to 10. Okay, so from the table, this is from table. The third slope is 0 decibels, which is 0 decibel per decade. Log of the present omega and the previous omega, and the previous value is minus 16.5 decibels. So you probably get the value at this becomes 0, so it's minus 60.5 be there. The third one is omega is chosen to be omega h, which is equal to 20 radians per second. 20 radians per second. So I replace the slope which is from the table last slope minus 40 into log of the present omega value 20 divided by the previous omega value 10 plus the previous magnitude value minus 16.5. I am getting it like minus 28.5, minus 28.5. Since it is not crossing your negative value, you started with the 3.5, so it is initially positive, then it goes on to the negative part. Okay, so it is crossing the 0 decibel line. What is being asked in the question? What is being asked in the question? The question asked here is plot the Bode plot, sketch the Bode plot for the given transfer function and determine the phase margin and gain margin. To determine the phase margin, I am supposed to know where 0 decibel line is being crossed. So I have to have a magnitude plot crossing from positive to negative or negative to positive. That change has to be there, right? So I keep an eye on that, and I am getting it like positive to negative is been happening. So I take it as it is. Now, as I said, now we go for the phase plot. So your transfer function is g of j omega. G of j omega is 0.75 by j omega, 1 plus zero point 0.2 j omega, and you get your 1 minus 0.01 the omega squared plus j omega into 0.16 omega. Okay, 0.16, right? So this is the term. So 0.75 you doesn't have a angle value, it is a real number, so 0 degrees. And this j omega term will have in the denominator, so you will have a minus 90. And in the numerator you have a 1 plus 0.2 j omega, so tan inverse of imaginary is 0.2 omega divided by 1, so you will get tan inverse of 0.2 omega. Then denominator term is minus tan inverse of 0.16 omega, which is from the quadratic term. And as I said, because of the omega value, if omega is chosen as 10, omega squared is going to be 100, and this is limited to 90 degrees. And if omega is chosen beyond 10, it goes beyond 90 degree. So a correction of 180 degree has to be done, which you can see that from your S plane. Okay, this is 90 degree, and if it goes beyond this, if you are an obtuse angle, then you have to add 180 degree plus the tan inverse of that angle to get your angular value. So you add a 180 plus term for this particular term, right? So tan inverse of 0.16 omega by 1 minus 0.01 omega squared plus 180 degree for omega greater than omega n. And if you apply different values of omega around the corner frequency, which you have got from your transfer function, you get different values of phi there. So minus 88 to minus 174. Even if you put 1000, you are not getting the values nearer to minus 180 degree. So it is not crossing that minus 180 degree mark, which will help you in dealing with gain margin. So if I take these points, let us say I will make a table as I normally do for this magnitude. This is omega and a in decibels and different values of omega. Initially it starts from 0.5. At 0.5 it is 3.5. At 5 it is going to be minus 16.5. At 10 it is also again minus 16.5. And at 20 it is going to be minus 28.5 decibels per second. Okay, so this is the value. Okay, if I mark these points in these graphs at 0.5, so I choose it like 0.1. Okay, this is 1, this is 10, this is 100, this is 1000, and this is going to be 10,000, right? So at 0.5, this is 0.1, so this is going to be 0.5. At 0.5 the value is 3.5. At 5 the value is okay minus 16.5. Minus 16.5 is available here. If I take a scale of, okay, this is 10, this is every y axis has one unit to be 5 decibels, so this is 5 decibels. This is 5 decibels. Okay, so 10 decibels is for every 10. One line is 0.5. So I will get like minus 10, minus 15, minus 20. It goes on up to minus 28.5 unit, right? So we have it like this. So if you mark all these points and join the lines, and probably you will get a crossing of 0 decibel line nearly here, which is nearly 7.5. B, this gain crossover frequency omega GC, gain crossover frequency omega GC is equal to 7.5 radians per second. Okay, and the phase plot, if you plot all the points as you take for omega from 0.5 to 100 or 200, whatever it is, and if you sketch them, if you join those points, you will get a plot like this. Okay, and now it is time to, this is your magnitude plot and this is your phase plot. This is a phase plot and this is your magnitude plot. Okay, so if you want to find the gain margin, phase margin and all, first we will start with the omega GC point. Omega GC is 7.5 radians per second. Extend that line downwards where it cuts your phase plot, and you try to find what is the corresponding angle value. You can see that here you are getting 5 GC is equal to 88 minus 88 degree. So what is your phase margin? Phase margin is gamma is equal to 180 plus 5 GC. So 180 degree minus 88 degrees will give me 90 degrees. That is my phase margin. Okay, how to find your gain margin? Gain margin, try to draw a line from minus 180 degree line, minus 180 degree, and we have already noticed that from minus 180 degree you are not getting any point actually, even if you vary your omega value to any even 10,000 or 1,000. So it is around that 175 178 mark. It is, maybe we assume that it reaches this minus 180 at infinite. So your gain margin will be infinite. Gain margin will be infinite. So what is that? I can conclude the system is stable as your phase margin, as gamma and gain margin are positive. System is stable. If any of this is negative, then your system is unstable. It is unstable, and your phase crossover frequency cannot be found because it is not crossing your 180 degree mark. So with that, I think I have completed this problem. Uh, we will meet in the next lecture. Thank you very much.